Hi there, and welcome to this lecture on process flow diagrams, equipment symbol representations. My name is Marina Milicic. This group of symbols is also a cornerstone in almost every chemical process. They're towers, specifically a class of separation equipment which includes distillation, absorption, adsorption, stripping, and liquid-liquid extraction. The letter abbreviation for towers is T. This first symbol is a simple tray column and is one you might commonly see in many chemical processes. The dashed lines represent trays, but you might see symbols with solid lines as well. This second symbol features large X's in two sections of the column, which means it has packing which was dropped in from the top and is most likely supported on mesh-like trays. Packed columns can be used for all the processes I've mentioned a minute ago. This third symbol is used for two-stream continuous flow separators, such as absorption columns, stripping columns, and liquid-liquid extraction columns. These can be tray or packed columns, but the one shown here has trays. With these types of separators, you're separating chemicals from one stream using another stream. This last symbol here represents an agitated column, which uses a stirrer to turn an agitator inside the column to facilitate separation. This is best accomplished with a column that has trays. The types of separators for which this is most effective include absorption, stripping, and liquid-liquid extraction. Because of the type of separator this column represents, this symbol almost always should have two streams coming in and going out of the process unit, as shown here. But it sometimes is also represented like this, with one stream coming in from the side and two streams coming out. Before we discuss these separators in greater detail, something to note is that distillation columns separate one stream into two or more using heating, and more specifically, it separates chemicals using boiling. The rest of these separators use either a solid, liquid, or gas to purify a liquid or gas stream. So distillation uses heating to separate chemicals, and absorption, stripping, adsorption, and liquid-liquid extraction all involve using chemicals to separate chemical streams. This means that these spent chemicals need to be disposed or regenerated in some way after they've been used to purify the other stream. For this reason, you might notice that distillation clearly has some advantage over the other processes you see here, in that even if it's energetically expensive because it requires heating, it at least doesn't have to use other chemicals. This is why distillation is the most widely used separations process unit for homogeneous mixtures, and is one of the most common units you will see on a process flow diagram for large-scale gas or liquid separation. In the end, after you consider disposal or regeneration costs, distillation is usually the cheapest and most efficient method of separating chemicals from a liquid phase mixture. So I suggest that you always seriously consider distillation as an option when designing a separator for your process. By the way, you can also add chemicals to distillation to help facilitate separation, and this is called extractive and azeotropic distillation. Using these methods, you can add a component to the feed stream, shown here as C in blue, to help break an azeotrope or shift the bubble or dew point so that chemicals can be separated more easily. This additional chemical ends up in the distillate or bottoms and needs to eventually be separated from that stream. Let's look at some of these separation equipment symbols more closely and briefly look at how these units function. These are symbols for tray and packed distillation columns. Distillation uses boiling to separate homogeneous mixtures into two or more streams. This boiling of the stream occurs on every tray of the distillation column. The more volatile components vaporize and rise to the top of the column, while the heavier, higher boiling point components are separated from the bottoms. Distillation is one of these processes that requires a vertical column. Some separation units can operate as rotating drums or horizontal beds, but distillation works through vapor rising and liquid falling, so there must be a vertical column. So distillation will always be designated as a tower on a process flow diagram. Also, since components are separated by boiling them, there must be a difference in boiling points between components in order to effectively separate them using distillation. Let's next look at absorption separators. These are representations of tray and packed absorption towers. Notice these are slightly different from distillation columns in that they have two streams coming in and going out of the tower. So we can better understand these process units, I'm going to remove the internals from this tray column for clarity. An absorption unit uses a liquid to clean a gas. The liquid can be sprayed from the top or simply sent into the column using a pump. The gas, because it's lighter, is bubbled in from the bottom. So the gas almost always moves countercurrent through the liquid in the column, and by the time the liquid exits, it will have dissolved and transferred some component from the gas phase, leaving the gas cleaner than when it entered. The spent liquid is collected at the bottom and must either be separated further or disposed. Because this separation technique is based on solubility, components being transferred must be more soluble in the liquid phase compared to the gas. And as you might guess, a common liquid used in absorption is water. Let's next look at the process, which is essentially the reverse of absorption. Stripping columns can be tray or packed towers. The purpose of a stripping column is to use a gas to clean a liquid. Like absorption, the liquid can be sprayed or pumped and flowed into the column. Clean gas moves up the column while contaminants are transferred to it from the liquid phase. This results in a clean liquid exiting the column at the bottom and the gas with the contaminants leaving from the top. This spent gas is usually vented or further separated. As with absorption, because solubility is the driving force for this separation, components being transferred need to be more soluble in the gas phase compared to the liquid, otherwise the liquid won't be purified. Common gases used in stripping columns include steam and air. This next process unit is used extensively for large and small-scale cleaning of liquids and gases. Adsorption units use solids to clean a liquid or gas. For this reason, a packed column or a packed bed must be used. In the case of a vertical tower, this packing can be supported on trays or for a horizontal bed placed in tubes or in a horizontal cylinder. No matter what kind of configuration, for adsorption units, some solid material must be used in order to adsorb contaminants from the process stream being sent through. Liquid or gas is sent through the column and is passed through the solid adsorbent packing. This solid preferentially binds to some adsorbate which needs to be removed from the process stream. And the liquid or gas leaves the process unit cleaner than when it entered. Because of the nature of this type of separation, the solid needs to preferentially and specifically bind with or trap whatever component needs to be removed from the liquid or gas phase. Notice that only the process stream is shown here. However, periodically the packing needs to be removed and either regenerated or landfilled. Examples of solid adsorbents include activated carbon, which is frequently used for purifying water, silica, and various clays. This last separation process unit, liquid-liquid extraction, is another method for purifying liquid streams and can use either tray or packed columns. Liquid-liquid extraction is a separation method where one liquid is washing another liquid. In order for one liquid to clean another effectively, the two liquids must be immiscible and of different densities. Also, because this separation technique is based on solubility, components being transferred must be more soluble in the solvent phase, the liquid doing the washing. Otherwise, the contaminant will not leave one liquid to go to another. If any of these criteria is not met, this separation method will not work. The two liquids enter at opposite ends of the column, the heavier, denser liquid being pumped and introduced from the top, and the lighter, less dense liquid sent through the bottom. Since these liquids are immiscible, the bubbles in this diagram signify one liquid bubbling up through another liquid. These two liquids flow past each other countercurrently. The process fluid exits the column, and the spent liquid solvent must be further separated or disposed. Notice this setup shows the heavier liquid initially having the contaminant and it's being washed by the lighter liquid. But it's just as common to have the heavier liquid as the solvent and the lighter liquid initially with the contaminant. Common liquids used as solvents in liquid-liquid extraction include water and hexane. Let's next look at how these separation equipment units are represented in ChemCAD and Aspen. This symbol is the default distillation unit for ChemCAD, and this one is the most common distillation column symbol in Aspen. Notice both of these already include condenser and reboiler units, so you don't necessarily have to design these as separate heat exchangers when building a process flow diagram in ChemCAD or Aspen. The ChemCAD symbol is used quite frequently, but in terms of Aspen symbols, there are a couple other variations for separations processes. These drawings are similar to the symbols available in Aspen for specifying tray and packed columns in case you feel the default unit doesn't visually describe the process unit accurately enough. Incidentally, the one distillation column symbol that's most physically accurate and best represents what a distillation column looks like from the outside is this one from Aspen. Most distillation columns are basically a cylindrical shell with some pipes going up and down the sides, and the whole column is almost always covered in insulation. One thing that is not accurate about these drawings is that condensers are not usually at the very top of the column as they're usually drawn. For some very tall columns, this would mean that they would be mounted on supports 150 to 200 feet in the air. Not only is this dangerous and makes the unit difficult to access and service, but it's also unnecessary because reflux can be pumped back up to the top of the column fairly easily. So many very large condensers, such as the ones that are in refineries, are either on the ground or, to save on space, elevated 1 to 3 stories, but not much higher. Similarly, reboilers are usually placed on the ground since this allows the bottom stream to flow by gravity to the heat exchanger, and vapor can rise up to the base of the column.